I think we're live already now. I think we can start. Thank you so much for joining our live stream. If anyone was attending our last stream, welcome back. If you're here for the first time, thank you for joining. My name is Anya, and I'm a business development manager of KMINE. And today we will talk about our updated scheduling model. So here with me is Vitaly Drozdov, who's a senior mining engineer in KMINE, and he was actually in charge of developing new features in this model. He will answer your questions at the end of the stream. Vitaly, are you here?
Yes, I'm here. Hello, everyone.
Okay, perfect. Well, as usual, this stream is being recorded. So if anyone missed live webinar, they will be able to see the recording later. If you're familiar already with the KMINE product, you know that we have many models that cover a full mining cycle from exploration to the production stage. And we do have models for open pit and for underground mining. And today we are going to talk in more detail about the specific functionality and purpose of scheduling model for open pit. So even though our mine planning is similar to the planning that other companies do, it has its unique features that really depend on mineral resources. And once we start mining, we constantly gather information about the deposit, and our knowledge grows about the site with every performed activity. At the end of the mine planning, the enterprise should receive a solid business plan of deposit development, and that includes a mining plan in a form of a production schedule with an origin, use, and corresponding quality of various rocks that have to be extracted from the deposit at the specific time period. So basically, mine planning is the process that optimizes the development of mineral reserves so the enterprise can get the maximum surplus value that would be aligned with the company's strategic goals. All the activities within this process are directed to the search for the best design, for the best production schedule, and that includes taking into account capital investment, operational costs, revenue forecasting, and company cash flow management. Overall, the goals of mine planning can be divided into three object groups: open pit, mining equipment, and processing plant. Each of these goals has corresponding sub-goals, and our goals for the open pit are considered reached if things like maximization of performance, net present value, and ore extraction are achieved with minimum work during the preliminary period, and minimum production costs, waste extraction, and transportation distance. Additionally, during this time, there should be a balance of the principle first ore, then waste, and the overall balance between the angles of pit slope and the economic indicators. The goals of the mining equipment consist of the optimized plan of equipment repair with improved skills of personnel that operates this mining equipment. It's also important to maintain the appropriate level of material reserve and balance the ratio of the equipment availability and plant capacity factor. The other goals of the mining equipment are things like proper determination of the optimal life cycle of each piece of equipment. And that means that equipment indicators like factor of technical availability, equipment utilization rate, and efficiency of mining equipment repair services, all of these things have to be maximized. As for the processing plant, its goals consist of production boost of processing facilities and plant efficiency with minimum waste and minimum cost of processing raw materials. It's also important to maintain a constant flow of ore in sections and make sure that the plant can respond promptly to changes in the quality of supplied ore. Of course, each of the goals that I mentioned is highly complex and the result can be enhanced continuously. But let's start talk about the planning process overall. It starts from strategic long-term planning, which determines strategic goals and opportunities, and then it moves to the midterm planning, and it creates usually a schedule for the next 5 years. During this period, the main goal is to find ways to reach the strategy that was defined in the previous stage. And finally, the short-term planning is created for up to 2 years. And during this period, we need to determine the specifics of each piece of equipment in the considered period of time. So in the end of operational planning, we will have tasks that are breakdown by shifts of each piece of equipment. Every stage of planning inherits certain digital information like surfaces and lines, tabular data of types of rock and mass excavation volumes with their quality specifications. Once the planning stage receives this data from the previous stage, it transfers it to the next one. And today we will focus on how to achieve the expected result when you do midterm planning, and we will see it in our updated schedule model. So, as I mentioned before, the midterm planning usually means a period not longer than 5 years. However, it really depends on the deposit size. Let's say for small deposit, it might be even shorter, and for big ones, it can be up to 10 years. The foundation for this phase is the data from the previous planning stage that is called life of mine. The mining direction will be determined by the surfaces from the periods of life of mine plan and mining calendar. We can use the same pushbacks that we had for the previous scheduling stage, and the block model should include the sample results from the exploration block model. The schedule calendars are also created the same way that it was in the plan of the life of mine. And it is in the same direction, but the plan is enriched with different clarifications like capabilities of excavation and loading, transportation, drilling equipment, excavators placement in the main mining areas, opportunities for pit sinking and others. Plus, we have specified areas of overburden dumps backfilling with mining waste. It's the stage of midterm planning that indicates the start of the detailed calculation of the transportation of rock mass, indicating the main roads, points of loading, unloading, speeds of rolling stock. And it also becomes clear if there is a lack or there is excess of equipment. So this process is generally called track study. Today, we're gonna review several options to reach the goals using only one variable of determination of separate mining areas. And we will see how this variable affects the planning results and what are the positive and negative aspects of adding and deleting sections. All data that we're going to use in this demonstration is artificial. So it was created specifically for this webinar. We have a block model with a regular block size of 10 by 10 by 10 meters. And as a mineral, we use iron ore with the quality indicators of ferrum total and ferrum concentrate. The rocks with the rock code number 2 are considered high-grade ore, and the rocks with the rock code number 4 are considered low-grade ore. And all other rocks are defined as waste. All right, so if we just start our presentation here. 1 second. Okay, So all block model is colored according to the raw code attribute. So you see that the high-grade ore is located in the center of the open pit, and the low-grade ore is located closer to the western pit wall. So basically, if we take a deeper look to the ore bodies, we will see we will need to display only a useful mineral, and basically it's enough to set a limit for the sort attribute and make it greater than 0. So there are two bodies, ore bodies on the screen, and if we reset visualization settings of the block model, we can take a look at the group with initial data. So if we take a look at the next type of initial data, it's provided in the form of surfaces. It's called pushbacks. Basically, the main goal of planning on this stage is to determine the rational sequence of mining sections within and between pushbacks. As all the data is superficial, we can say that we just receive it from the previous scheduling stage. And we can just start the first scenario. We just run a scheduling command from the planning menu, then use the command new project, and we just name it and place it on the local disk where the data is stored. So as the next step, we're going to add a block model to the project body. And in order to do it, we just use a special icon on the toolbar, and we specify the name of the block model and the layer where it's stored in the main ODF file. So then the software will offer us to customize the existing block model, so we can use it in this model. And all data will be saved within the block model, and it will be checked for errors. We specify the layer where the customized block model will be located and stored on a computer, and the program will create a separate ODFB file. So there are two ways to determine the block weight parameter. We can use the block mass, and in this case, we work with a prepared attribute in the weight of block model. Or we can use a specific weight. That means that we would work with a specific rock weight that is multiplied by the block volume during the calculation. In the block model, this attribute is displayed as density, and so let's choose this option. So the last step of block model setting would be to determine the surfaces between which the calculation will be made, and we just select them in the layer editor. And we can hide or display its part that should be scheduled. So we can just display the bottom surface of the planning for better visualization, and we see that the displayed blocks correspond to the surface. Perfect. So let's define the rock types to select them separately when we are configuring this scenario. In order to do that, we add in 3 rock groups where the rock classes will be located according to the material class attribute. So we name them high-grade ore, and this rock type corresponds to the rocks with the rock code 2. We add qualitative indicators of ferrum total and ferrum concentrate that are also unloaded on the from the block model. So let's add another rock class, which will be low-grade ore. And this rock type corresponds to the rocks in the material class attribute number 4. We adding qualitative indicators the same way we did before. And we can just specify all other rocks as waste and apply them. Okay, and we can just see the result. The total weight of rock mass is to be scheduled about 49.5 million tons. The high-grade ore is 9.4 million tons. The low-grade ore is 8.4 million tons, and waste is 31.7 million tons. We also have the average quality characteristic of each ore type and the volume of all rock groups. So the next step is the most essential one to customize the scenario. It consists of the identification of the scheduling areas, and we are going to focus on it today. In this scenario, we will see how the excavation volumes react if there is only one planning section. Let's define it using just a built-in tool, and interactively we can select points on the screen that are all blocks that should be within the boundary and apply it. You can see the table automatically displays the level of all rock groups that were previously defined. And if we move to the section configuration, we set the stop width, stop tolerance, and site width as 30 meters. So now let's configure the scheduling intervals and specify them by 1 year from now and for 5 years ahead. So as target indicators for mineral, we use qualitative indicators, setting a range. And let's set the target indicator of 2 million tons for high-grade ore weight interval. The tolerance would be 200,000 ton at 10% level. With this initial data, the software will stop the search when the weight of high-grade ore reaches 1.8 million tons. So we click and calculate and see the result. And as you can see, the mining started from the top and the sequence indicators are not violated. Now, about volumes, the total weight of rock mass is about 6.5 million tons and ore weight is 1.8 million tons. Also, we can just adjust the resultant table so it would display columns, and we can just select or hide them from the available list. So let's set the same target values for the next periods. In our example, we're going to review two main indicators, the total high-grade ore and the total weight of rock mass. So usually these two indicators are the main ones that you need for production tasks. There are also cases where you're required to minimize low-grade ore, and of course, the more target indicators are set, harder it will be to be able to obtain the required effect in the scheduling process. So in order to minimize low-grade ore, we need at least to construct specific pushbacks. By changing the intensity, it will be possible to delay the extraction of low-grade ore for later. And as our schedule starts shaping up, we are checking if it's possible to be mined or not. Okay, so here we are setting the same indicators for each interval. And we see the calculation. So if we select the intervals, all blocks for each interval will be visualized. And we can see that the mining process did not reach the bottom as it was focused specifically on ore excavation. The bottom of the open pit is a bit shifted towards the west side in relation to the main ore deposit. So this pushback covers pre-stripping for future pushbacks. So let's take a closer look at the tabular data, and we're exporting them into Excel format, and we just create charts for better visualization. So we can visually see and evaluate the preliminary scheduling results in Excel, and we see that the software fully meets target indicators and was focused only on ore extraction. The total weight of rock mass is variable and reaches maximum values in the second and fifth period. It is understandable because the task was to accumulate only the ore volume. As the ore was in the stripped state, it was provided the minimum. It provided the minimum waste during the first period. So in the end, we get the peak value of waste in the last period because of the progressively accumulated waste depth. One of the main tasks of the planning is to define the optimal balance between the indicators of ore and waste. And having a certain fleet of equipment on the enterprise, it's not profitable to operate in one period at 50% capacity. If it operates at the capacity of, let's say, 150%, we need more equipment and contractors. So in this case, the schedule is not feasible. Now about settings and the speed of the scheduling process. As we saw, we got the results very fast, and fortunately you can draw the average lines and find out how much waste each period should have in order to work on ore within the required schedule. Also, we can see that the direction of mining work is to find ore on the subsurface. Having that information, we can find the load intensity on each sections that we must identify. And in the end, this approach gives us the fastest results and helps us to preliminary estimate and analyze the status of mining operation. So now we are trying to force digging more in each period so we can average the data on the transporting rock mass. We'll try to reach the level of a total 10 million tons of rock mass in each period. We will select different values that help to meet target indicators. Okay, so if in the first period we reached 9.5 million tons of rock mass, and at the same time, the volume of transported ore increased from 1.8 million tons to 2.2 million tons, according to permissible deviation. Now we're doing the same thing with the rest of the periods, and we're trying to extract more rock mass in each period. As for influence leverage, we can use low-grade ore and waste mass target indicators. In this scenario, we will review the most straightforward method, which is the most efficient one, as well as we are going to increase the transportation volume from the whole section. So as a result, we got 9.5 million tons in the first period and 8.5 million tons in the second period. 8.9 million tons in the third period, and 9.4 million tons in the fourth period. So in each period, the indicators of high grade ore transportation increase with permissible interval. Therefore, as a consequence, there will be not enough ore volume left for transportation in the last fifth period. The indicators of rock mass transportation have totally amounted to 9.3 million tons and 0.9 million tons of high grade ore. Okay, so we can take a closer look at the result using just Excel, as it's more understandable when it's visualized than it's cold numbers. So let's see it in Excel, and just visualize it, and we see that the ore volume is constant until the fifth period, and because in the fifth period there was not enough ore. But we can see that overall the rock mass volumes are distributed smoothly over the periods, and there is only a slight drop in the volume of rock mass transported in the second period. And also we can see that the volume of transported low-grade ore increases as the open pit deepens. This pushback is turned by the bottom specifically on this type of ore, and we can assume that the next pushback should be in the section towards the east, since the west has already been sufficiently exposed by the main ore. Now we're creating, let's create a new scenario. We're gonna name it and pick the storage location on the local disk. And then in slightly accelerated mode, we will review the same operations that we had in the first scenario. We just define the class attributes, surfaces, and add row groups. So in this scenario, we are going to try to split the available blocks from the block model using the built-in tool. This tool is perfect for these types of conditions because if you need to divide work areas, for example, for several equipment pieces in a single pushback, that's where this tool is very useful. Let's create 4 arbitrary sections, north, south, and at various elevations. And the screen will turn to the top view if you need to select each subsequent segment. Only the blocks that will be available will be the ones that were not included in the distribution of sections in the previous stages. So we're gonna take a look at each of the defined section closely. Just finish up here. All sections are split by a vertical line, but as we know that they can be used to split the work of excavators in a single pushback. Besides, it's much faster than building individual pushbacks, and we'll talk later about the process of adding proper pushbacks to the project body. So now let's try to reach the most even regular rock mass transportation from the open pit with the same target indicators. And in this case, the qualitative indicators were not added to the project. We analyzed in which section to carry out works, decreasing the intensity on each area in a certain period. We're going to reach the following results. You'll see it on the screen in a moment. Okay, so now we just gonna export it into the Excel file and we're gonna review it in chart version. And we can see that the expected result was reached only in 2 periods. In this case, splitting into more sections did not provide a beneficial outcome. And the current status of mining works is due to transport berms in each of the levels. So it gradually increases the volume of rock mass with the lowering of each level. This factor is evident when you compare the scheduling results of 2 scenarios. And in this case, splitting into more sections is not necessary to achieve the result that we actually wanted. So now we're going to review the third scenario. The third scenario would be the most common way of defining sections because it describes the correct boundaries between sections. But in order to activate it, you will need to prepare some pushbacks in advance. So to define individual pushbacks in order to demonstrate this scenario, and using set properties command, we can select pushback attribute in the block model field. Individual blocks that correspond to the particular pushbacks will be displayed according to the specified number, and as a result, there are 4 surfaces and 3 pushbacks. So let's configure this scenario in the same way we did in the previous scenarios. We name it, locate it, and define the block model settings. So when the section configuration changes, we're going to select the load from the block model command, and in the attribute section line, we select 3 pushbacks. So let's select raw groups as we did in the previous scenarios without specifying qualitative indicators, since they are not required in this scenario. We set the parameters to configure sections and intervals. And in the current scenario, we specify the high-grade ore target as 1.8 million tons and rock transportation of up to 9 million tons for the period. And now we're going to see how to search for the result using another target indicators, which is waste transportation. And we're going to set it as 8 million with a high deviation rate. So we would not prevent the search algorithm. And we're going to do the same for other periods. Just when we define only target indicators, and when it's not enough, we will use force loads on each of the pushbacks. This method ensures that it is physically possible to reach the mining position as it is based on actual previously drawn mining positions. And we should use the pushback method to get the most accurate scheduling result. So now we're going to export the results to Excel and generate chart. And given the fact that drawn pushbacks are used, the charts looks even. And it's reasonable to assume that the schedule is feasible. And now we only need to set up the equipment and see the result. So basically today we saw how the optimized algorithm is for searching optimal solutions, how to solve the task fast. And you can see that the new mining schedule model of KMINE can be used for short and long periods of time. So now let's see if we have any questions here. I do want to give the floor to Vitaly, as he's the one who will be answering questions. Vitaly, are you here?
Yes, sure, I'm here.
Okay, perfect. So I see that there is a question. How accurate is the developed plan compared to actual real world situation, and how does it adapt to represent the actual situation?
Okay, thank you for your question. So the plan corresponds as much as possible to the period from which the planning begins. It is clear that during operations there may be some unplanned mining activities. In this case, a decision is made when the initial data have been significantly changed, and it's better to revise the plan.
Okay, so another question is how to optimize the final pit and maximize overall net present value. Is the resulting mine plan correct?
Okay, thank you for your question. So the optimization of the NPV indicators process is the most important at the stage of long-term planning. In the Pit Optimizer module, we propose to consider different options of the final contours with the adjusted price factor. Based on the obtained data, we will get a set of data for analysis. We suggest you to look at the previous stream related to the capabilities of Pit Optimizer module.
Okay, perfect. And the other person also asked, what is the solver used by KMINE scheduling?
Mhm.
I don't know what it means by solver, do you know?
Sure, I know what it means. Actually, I can't remember how it names, but I know how it works. So
Okay.
it's some. It created before the start. It created some specific relations between the different blocks, and when it start working, this solver, it could be defined only the one right solution. So this process, some like searching for the very best solution of mining sequence, something like that.
Okay, well, thank you so much. Thank you for your answers. And thank you guys for attending this stream. We'll send all the attendees the recording of the stream. Please comment your feedback about the stream below. Today was not as smooth as it was before, but we can only try to be better. So let's take it into consideration, and don't forget to follow our LinkedIn page, and hope you guys to see you again in the next live event. Bye.
Okay, thank you. Goodbye.